city. So let's take a closer look at this graph, and suppose if you want to calculate the shortest distance from to every other node in this graph, this can be easily done with this algorithm. So we just have to keep look through this algorithm. The first information here is which nodes we have not visited yet. So in the first step, we mark all nodes as unvisited. So create two lists, a list of unvisited nodes and visited nodes. So in every node in the graph and also visited nodes, that is empty in the beginning. So in the second step, we assign to all nodes a tentative distance value that will be changed over time. So therefore, we can use this table on the right, which consists of three columns. In the first column, we have the node. Second column, we have the current shortest distance from to this node. So in the beginning of this algorithm, we know nothing of any distance to any other node. So then we set to 0 because the distance from A to A is 0, and every other distance we set to infinity. And in the last column, we store the previous node that lead us to the shortest distance, and this column will be empty in the beginning because currently we have no information about this. So these are the things we need to keep track of, and now we can start with the first iteration. So we start at a node A by start by calculating the distance to all unvisited neighbors of the distance from A to B is 2. So and from A to D is 8, and now we can update our table on the right. So if we found a new shorter distance to one of the unvisited nodes, so B and D are unvisited and the current distance is infinity. So we can update the distance from A to B as 2 and store A as the previous node in our table, and the same applies to the node D. So we can update the shortest distance to D to the value of 8 and with the previous node A. And now our iteration ends here. And we can mark A as visited, remove it from our unvisited node. So in our visited node list, the last step we didn't talk about it, the new node as a current node to explore this graph further. And therefore we always choose node with that current minimal distance in all our unvisited nodes. So when you look at the table, we have with a distance of 0, but A is already visited. So we have B as unvisited node with a distance of 2. So we have D with a distance of 8. All other nodes have distance infinity. So B has the current shortest distance of all unvisited nodes. This means that B becomes our current node for our node B. So we can now go back to our step 3 to calculate the distance of all unvisited neighbors of B. So unvisited neighbors of B are E and D. So on the distance calculation works as follows. Since B has the current distance of 2, we need to add this 2 to the weight of edges to E and D. So now let's first look at the node E. It will have the current distance 8 from A over B. So now we need to check if that value is less than the current shortest distance. So in our table, the current shortest distance we saw in our table is infinity, and 8 is certainly less than infinity. So we update the table with this short distance. So as a previous node, let's look at the node D. Will now have the distance of 7 to 5 from over A over B. So this means we need to compute our current value 8 in the table, and since 7 is less than 8, so we set the current value for the shortest distance to 7, and we set the previous node to B, and now we are finished with B. So because we visited all unvisited neighbors of B, and we can mark B itself as visited in the next step. So we now choose a new current node from all unvisited nodes again, and we choose the node with the minimal distance. So in this case, it's D because it has the distance of 7. We now calculate the distance to all unvisited neighbors of D. So in this case, we need to add 7 to this distance because currently the shortest distance from A to D is 7. So when we look our table, we need to consider, so if we need to update the distance to E or we need to update the distance. So let's start with E. The distance from A to E over D is 10 plus the 3. So that our current distance 8. So that we have stored in our table. So we don't need to update it. So when we look at the node F, on the other hand, here the value is also infinity, but now we get the distance of 9 from A to F over the node D. So we should update our shortest distance in the row F. So set it to 9 and set the previous node to D. So we can now mark D as visited, and we can go on with the next node in the unvisited list with the current minimal distance. And this will be E because E has the shortest distance of 8 and F has the distance of 9 and C of infinity. So we calculate the distance from E to C and E to F in this case. So here, because 8 is the current distance from A to E. So let's start with the node C. We now have a distance of 17 from A to C over the node E. So, and this is certainly less than infinity. So we can update our distance to C in our table. So set the shortest distance to 17 and previous node to E. So when we now look at F, we can see a new distance of 9 to F, which is exactly the same as our old distance to F. So we don't update anything and we are finished with our node E. So now we have F and C left as unvisited nodes. So F has a distance of 9 and C has a distance of 17. So we always start with the one with the minimum distance. So we start with the F and the only unvisited neighbor is C. And now we see that we have a distance of 12 from A to C and we go over with the node F. So we can update the shortest distance to C, setting the previous node as F and mark F as the visited and leave as with node C, since C has no unvisited neighbors, and we can mark C as finished. And now we have done with the algorithm in our table. So we have the information about this graph. We now have the shortest distance from A to every node in this graph and the previous node, which helps us to reconstruct the shortest path. So for example, if you want to reconstruct the path from A to C, the first thing is that the shortest distance is 12. So to find the shortest distance, so look at this previous node, which is F in the table. So we mark this node from F to C, and now we look at F and see it has the previous node D, and so we mark with this edge from D to F. So we now just need to look at the node of D in our table, and it has the previous node B. So we have marked it from B to D, and now we look at the node B in our table and see as the previous node as A, and we have found the connections from A to C that has the length of 12, so which is that shortest distance. Thank you for watching the video. Meet you in the next video. Goodbye from